Okay, continuing on with Chapter 2, Fluid Statics. The topic of this presentation is hydrostatic forces on plane surfaces, and this kind of analysis comes up in engineering design when you're looking at things called, I'm going to call it liquid containment structures, things like storage tanks, dams, levees. It's also important for determining the forces on the hulls of ships and things like submarines. Okay, and here's an everyday application of this concept. What I'm showing here is a picture of domestic water storage tanks. They're put at the top of buildings. This is in New York City. They have a lot of these tanks that are made out of wood planks, and you'll see these steel rings, these steel bars that go around. And if you look closely, you can see that they're unevenly spaced. They're widely spaced at the top of the tank and very narrow at the bottom. And you might wonder why. And of course, the reason is because of the hydrostatic pressure distribution, that the force increases linearly with depth. So you have a lot more force on the wood at the bottom than you do at the top. And you need these steel rings to be more closely spaced. Okay, so moving on to the analysis, what we're going to be looking at is, I'm showing over here on the right, is we have a reservoir of fluid, usually of liquid, usually water. And so we're going to be assuming an incompressible liquid contained in a reservoir behind some sort of gate structure. So we've got a linearly increasing pressure with depth. The pressure just increases as gamma H, the gauge pressure on the gate. And of course, the pressure acts normal to the bounding surface. And so the goal for this analysis is we want to integrate the pressure distribution over the gate and find the total force on the gate. And we also want to find out the line of action, so where it acts on the gate. And of course, that would be a precursor to stress analysis in order to size the thickness of the plate required to not bend under the force of the water. Students sometimes have trouble visualizing this problem, so I wanted to first show you a oblique view, a 3D view of this gate problem. So what we have is a reservoir of liquid, usually water, and the free surface meets with the wall here, and the gate is in the wall, and this wall forms an angle theta with the free surface. That would normally be 90 degrees, but not always. The red outline here, sort of pinky outline, is the outline of the gate, and this spot here is the center of gravity of the gate. It's actually the center of area. I'm going to be using those terms interchangeably. Center of area and center of gravity for the gate would be the same if it was a uniform density thin plate. You will have run across and done some calculations of center of area in PCS 211. So as I mentioned, the objective is to find, for an arbitrary gate shape and location, you want to find the total force on the gate and find the location of the total force, which is called the center of pressure. So here's the mathematical analysis of this. This is a figure taken out of your book. So we're looking a side view now. So this is an elevation view. Here we have the free surface, and we have this angle theta. So we have some retaining structure, and the gate is forming an angle, is at angle theta from the horizontal. And here again, the red line here is the gate, but you got to recognize that you're seeing a plan view of the gate. So you're seeing sort of a rotated sectional view of the gate. And this gate here has a center of area. So CG is the center of area of the gate. And we're going to define, and there's an X and Y coordinates relative to the center of area of the gate, or center of gravity of the gate. And then we're going to define another coordinate here. It's the Greek letter xi, and it's the distance measured from this point up here, from the free surface. So measured downward along the inclined wall toward the gate. So that's what this coordinate xi is. So what we need to do is we need to integrate the hydrostatic pressure distribution over the gate. We're going to consider a little differential area dA equals dx dy, and the local depth at that point is h of x and y. And so the pressure at that point is going to be the atmospheric pressure. Oh yeah, I should point out that we have atmospheric pressure acting at the surface. So we're doing this in terms of absolutes. So we got the atmospheric pressure, and then this is the pressure. Gamma h is the pressure due to the weight of the fluid times dA. And then what I'm going to do is of course substitute that into there, and we get this expression here. So we want to integrate the atmospheric pressure plus gamma h dA. Now we'll notice that the atmospheric pressure and gamma are constants. We're assuming this is an incompressible fluid, so we can move those outside of the integral sign. Also, the integral of atmospheric pressure dA is just going to be the atmospheric pressure times the area of the gate. Going to the next slide, that's what I've done. I've evaluated the integral of the constant atmospheric pressure over the gate, and then I've moved out the gamma to outside the integral. Now what we're going to do is we're going to express this term h dA in terms of this xi coordinate. Now you'll notice that this height here, h, is equal to xi sine theta. That's simple geometry. So what we're going to do is express the F equation in terms of xi. So we're going to substitute h in there, and we get PA term, gamma. I can pull the sine theta out. We just have the integral of the area of xi dA. Now it turns out we can relate this to the location of the center of area, or the center of gravity of the gate. Now you should remember from PCS 211 that a little bit about centroids, that if you want to get the x location of the centroid, it's 1 over the area, the integral of the area x dA. And just to refresh your memory, if you drew a line down here, that's the location, the x location of the centroid, then you'd have half of the area on this side and half of the area on that side. That's the definition of the x location of the centroid. And so we can imagine the xi location of the centroid relative to this point up here, measuring downward. So that would be 1 over area, integral over the area, xi dA. And so we can express this in terms of the location of the centroid relative to the free surface. So we multiply both sides by A, and we get A, the location of the centroid measured along the angle of the gate from the free surface. That's equal to this integral, which is this integral right here. We can make that substitution, and we just end up with that the force is this. We got this atmospheric pressure term, gamma times A, and then psi of the center of gravity, sine theta. Now I've moved the sine theta over to the other side here. The reason being is that this xi cg times sine theta is equal to the height of the center of gravity, because that's what we had. That's what we had here. And so now we can express this in terms of the height or the depth of the center of gravity. So the force on the gate is the atmospheric pressure times, and then this is the weight of the fluid, gamma times the height of the center of gravity times area. And of course, this is just the total pressure at the center of gravity that's caused by the atmospheric pressure and by the fluid weight. And so that's the resultant force on the gate. And you may have run across this issue before. The question then is, where does that resultant force act? So basically, we've replaced this blue, this is the pressure distribution on the gate, this ramped blue distribution. We've replaced it with a single force. So the question is, where does it need to act? What is the line of action? What's called the so-called center of pressure of that force? Now, you may have run across this issue before when you were doing deflections in beams, for example, if you've got a distributed load on a beam, if you replace it with a single force, you don't just replace it at the center of the distribution. In a ramp distribution, the net force acts below the centroid at something called the center of pressure. I'll talk more about why that's the case later in this presentation. But for now, it's important to remember that you calculate the force based on the pressure at the center of gravity, but that force always acts below the center of gravity of the gate. And there's more discussion of that to come. Okay, so how do you find this center of pressure, this location? We've got this blue distribution here. This is the actual pressure distribution on the gate, and we've replaced it with a single force F. And the way you find the location is that the moment of this equivalent resultant force has to be equal to the moment of this distributed force. And you can take it about any point. We're going to take it about the center of gravity. So if we're trying to find this distance here, ycp, below the center of gravity, then this resultant force times ycp, that's the moment due to the force, has to equal the moment caused by the distributed pressure distribution, which is this the blue curve. So PA gamma H times this local y dA. Now, this integral is it's a little messy. It takes probably a half a page to evaluate, but it's very straightforward. And so I'm just going to give you the result. The result is that the ycp, the distance below the centroid, is minus gamma sine theta is, again, theta is the angle up here between the free surface and the gate measured from the horizontal. Ixx is the second moment of area of the gate. I'll talk about that in a moment. PCG is the pressure at the center of gravity, and A is the plan area of the gate. A is just the total area of this gate. As I say, the details are fairly straightforward. We're just going to use that result. Okay, let me just say a few more words about this. So I've just rewritten the equation here. That ycp equals minus gamma sine theta Ixx, second moment of area, over the pressure at the center of gravity times the area. So ycp is measured relative to the center of gravity along the inclined gate. So, and I've tried to show that here. That's the distance measured downward from the center of gravity, but it's in the direction of this xi coordinate, measured along the gate. In most cases, it'll be a vertical gate, so it'll be vertically straight down. PCG is the pressure at the center of gravity, and Ixx is the second moment of area. Some people call it moment of inertia, but it's really the second moment of area about the gate. So about the horizontal axis Ixx. So it's measured along, it's the moment of area around this axis, which is actually a horizontal line. So it's from x. So it's the integral a y squared dA, which is just a geometric property. Similarly, if you want to find out the x location of the center of pressure, you do a similar analysis and you get a very similar looking expression. The x location of the center of pressure, so how far off this center line the center of pressure is, it's equal to minus gamma sine theta Ixy. I'll tell you what that is in a minute. Pressure at the center of gravity times area. So Ixy is called the product of area. It's analogous to second moment of area. It is a second moment of area, actually. But you have the moment in the x times the moment in the y direction, dA, called the product of area. Now, if you have a gate that's symmetrical around this axis, and that's going to be mostly the case when you have a gate that's symmetrical around that y-axis, then you'll find that Ixy is 0. That's going to result in a xcp being 0. So it'll be in line with the center of gravity. Now, luckily, you don't have to evaluate these integrals. Ixx and Ixy are given in a table in your textbook. Just to refresh your memory, because I think it's probably been a year since you did this, you probably did second moment of area calculations in physics, you probably did second moment of mass, which is moment of inertia, and you probably did second moment of area calculations when you did stress analysis in BME Mech 323. Remember that down here? I've written it. M over I equals sigma over Y when you did beam bending theory. That's the same sort of concept as second moment of area. So it's just the integral over the area of y squared dA, and it's available for the kind of shapes we need in figure 2.3 of your textbook, which I think is the next slide. So a lot of the times we'll be dealing with a rectangular gate, and for a rectangular gate, the second moment of area about the centroid through a horizontal axis here from xx is bh cubed upon 12, and I'm sure you've seen that before. It's going to come up enough that it's probably worth remembering. And you'll notice for the shapes that are symmetrical around the y-axis, like this one, that IXY is 0 and IXY is 0. And if you look at this triangular gate, if S here, if you set S equal to B upon 2 so that it's completely symmetrical about the vertical axis, you'll also find that IXY is 0. So the centroid locations and the second moment of area, normally around the horizontal, the x-axis is what you want. They're all available in tables, and we won't have to do those integrals, though I'm sure you've done those in other courses in the past. Now, sometimes you might be looking at a gate or a personnel access cover on a tank, and the inside pressure and the outside pressure is different. So then you would have to use the formulas that we just derived. But in many, many cases, and you're going to see this when we do problems, the pressure at the free surface, so the atmospheric pressure here, is the same as the pressure on the other side of the gate. So the forces due to the atmospheric pressure, they exist on both sides of the gate, and they cancel out. So in that case, you have a simpler version of these formulas, and these are the simplified equations, which are almost always applicable. You should keep in mind that if you have a tank with an internal pressure and you're trying to calculate a force on an access cover, then you need to include the internal pressure forces. But if it's just the weight of the fluid, then the hydrostatic force, this force on this gate, is just the gamma of the fluid, usually water, height or depth of the center of gravity, how far down you have to go down in the water or in the fluid to get to the center of gravity, times the plan area of the gate. And similarly, the YCP, the location of the center of pressure, again, relative to the measured downward relative to the center of area, is minus IXX. That's around a horizontal axis, sine theta, and then the depth of the center of gravity times the area. And you got to remember that YCP is measured, and I want to emphasize this, measured on an axis inclined at the angle of the gate. We'll do an example later on where we use that fact. So next I'm going to do just a really simple problem. This one is not midterm caliber, I would say. It's just a simple problem to run through the equations to get you used to them. And then in the next video, we'll do a more complex example. So here what we're considering is a reservoir of water that's 3.8 meters deep. And we're trying to calculate the force on this gate AB, which is 2 meters in height. And it tells you in the problem that this gate goes into the page 3 meters here, right? So it goes back into the page 3 meters. And so the question asks, A, sketch the hydrostatic pressure distribution on the gate, just on AB. That's a good idea. It's always a good idea to do that, get a physical sense of the problem. Then calculate the total force on gate AB, and then locate the line of action of that force relative to this upper hinge here at A. Okay, I thought I'd solve this problem on the tablet just for a change of pace. So this is just a very simple problem just to demonstrate using the equations, and you can try some of the more complicated ones in the problem set. And there's another more complicated one, more complex problem coming up in the next video. Okay, so part A asks for you to sketch the hydrostatic pressure distribution on the gate. So let me just re-sketch this here just quickly. Okay, so let me just change colors here to draw the pressure distribution. We know from the previous presentations that the hydrostatic force increases linearly with depth. So it would be 0 at the free surface and increase as we go downwards. And I'm going to draw arrows here to show the distribution on the gate. So that's the pressure distribution on gate AB. So pretty straightforward. Let me just put some more dimensions on here. So this is going to be 1.8 meters. Okay, the next part of the question asks to find the hydrostatic force on AB. And the hydrostatic force on AB equals the gamma of water times the height of the centroid, the center of area of gate AB, times the area of surface AB. And we should keep in mind that this gate, in the problem statement, we're told that this gate goes back into the page 3 meters. So the gamma of water equals rho of water times G, which at 20 degrees C, the rho of water, you can look it up, it's 998 kilograms per cubic meter times 9.81 meter per second squared. That equals 9790 newtons per cubic meter. That's the specific weight of water at 20 degrees C. You'll be using that a lot. The area of the gate is simple. It's 2 meters high and it's 3 meters into the page. So it's 6.0 meters squared. Now, we need to get the height of the centroid. The centroid of this gate is going to be dead center in the middle. Let me draw it over here, the centroid. And so that distance there is going to be 1 meter. So the depth of the centroid, HCG, is going to be that 1 meter plus 1.8 meters. So 1.8 meters plus 1.0 meters, 2.8 meters. That's the depth of the centroid of the gate. Of course, the centroid of the gate is actually over here. The centroid of the gate from the free surface. So FAB, making the substitutions, is going to be 9790 newtons per cubic meter. 2.8 meters times 6.0 meters squared. You can see we have newtons per meter cubed, and we have meters cubed on the top, so that's going to give the force 164,500 newtons. So 164,500 newtons, 164.5 kilonewtons. So that's the answer to part A, and of course it acts to the right. We can see that from the pressure distribution. We should also, forgot to point out, make sure when you're drawing these, if you're drawing them on a midterm, that you show that you're careful to show that the pressure vectors are perpendicular to the surface. So the next part of the problem is to find the center of pressure, or the line of action. So we want to find out, it always acts below the center of area. We need to find out what that distance is. Let me go to the next page. Okay, and I'm just going to take a second to draw this gate in 3D. Okay, so what we're after is the location of the line of action relative to the centroid. And we showed in the previous derivations that the YCP, the Y location of the center of pressure relative to the centroid, is minus IXX sine theta H of the center of gravity times the area of the gate. And remember, this negative sign is telling you that the location of the center of pressure here the force is going to act below the center of gravity, which is the center of area. So to calculate YCP, we need to calculate the second moment of area. So we need to calculate the second moment of area about a horizontal axis, this axis here, XX, which passes through the center of gravity. And you should recall that IXX is the width of the surface for a rectangle times the length cubed divided by 12. And so we have a gate that's 3 meters into the page, 2 meters high, so that's 3 meters times 2 meters cubed divided by 12, and that works out to 2.0 meters to the fourth. So now we can calculate YCP. It's minus 2.0 meters to the fourth. That's IXX. Now we next have sine theta. Now sine theta is the angle if you project the gate up to the free surface here. It's the angle that the gate makes with the free surface. And in this case, it's a vertical gate, so theta equals 90 degrees. And the sine of 90 degrees is going to be 1. I'll just write it in there just to let you know. And we previously showed that HCG was the depth of the centroid from the free surface was 1.8 meters. And the area of the gate is 6.0 square meters. You can see we have meters to the fourth on the top and meters cubed on the bottom, so that's going to give you minus 0.1190 meters. So we're 0.1190 meters below the centroid. So just to be clear, let me go to the next page and just make a little drawing. So I'm going to draw the gate again here because the question asks to locate that force. So here's the hinge. So the force AB acts at 1.119 meters from hinge A. And that answers part C. Okay, just to finish, I thought I'd talk about a question that often arises. Students often have the concern about why the center of pressure is below the centroid. Why doesn't it act at the centroid? Well, to try to give you a physical feel for this, I'm going to describe two cases. So first, let's consider a container over here that just contains gas. So let's say air, slightly pressurized air. And we're trying to calculate the pressure force on this gate here. Now, in this case, if you think about the pressure distribution on the face of this gate, it's going to be uniform, as I've shown over here. Now, why would you have a uniform pressure distribution in the case of a gas? Think about that for a minute. Okay, so the reason is because the density of gases are, typically 3 orders of magnitude less than liquids. This issue came up when we talked about manometers. The variation of pressure with height is often considered negligible unless you're over very large distances. So the pressure distribution here is uniform. So now, think about the moment of this pressure distribution around the centroid. You've got exactly the same clockwise moment above the centroid as below the centroid. So you can replace this force, this distribution, with a single force at the centroid. Both this equivalent force and the pressure distribution here have the same moments about the centroid, which in this case happens to be 0. So we just replace the force with the average pressure times area, and it would happen to be at the centroid. That's straightforward. But now let's return to the case where we have a non-uniform pressure distribution, because when we have liquids and we're considering hydrostatic pressure distributions, the pressure distribution ramps up linearly here. So now we're considering a reservoir with say water, so we'd have a linear pressure distribution on this gate. And so now we have more force on the bottom half of the gate than on the top half of the gate. The average pressure, because it's a linear distribution, is still at the centroid. So we still replace this with an equivalent force equal to the average pressure times area, which is the pressure at the centroid. But now think about the moments of this pressure distribution around the centroid. You've got a clockwise moment caused by this part of the pressure distribution, but it's going to be a lot less than the counterclockwise moment of the lower part of the pressure distribution. So the net moment of this ramped pressure distribution around the centroid is going to be counterclockwise. And so when you replace this with a single force, which is what we're doing, we're replacing it with a resultant force at the center of pressure, we place it below the centroid because this pressure distribution has a counterclockwise moment about the centroid. And you find, of course, the center of pressure is the location where it has the equivalent counterclockwise moment as the pressure distribution. You've probably run across this problem or this issue before when you were considering, ramped distributed loads on beams, when you were doing, moment diagrams and beam deflection calculations in your stress analysis course. So I hope that helps clarify why in a hydrostatic pressure distribution, the center of pressure is always below the centroid. Okay, and the next video involves a more complicated example where we have a reservoir with an inclined gate, and this gate happens to be semicircular. And so this involves a bit more complexity than the example that I just did. So have a look at it. It's more exam caliber. And so that completes this presentation.